Welcome to Frank Stajano Explains and the Formal Languages part of the Discrete Mathematics course at Cambridge. Last time I showed you how, given any NFA-epsilon, you could build a DFA that was equivalent to it using the subset construction. Today we're going to convince the skeptics that the two automata are indeed perfectly equivalent. We're going to prove an important theorem that's made of two parts. In the first part, we prove that every string accepted by the NFA-epsilon is also accepted by the DFA we constructed. In the second part, we prove that every string accepted by the DFA we constructed is also accepted by the original NFA-epsilon. That's really cool. If you think so too, say it out loud by clicking the like button.
So, with that understood, you should now prove that the language recognized by this machine is exactly the same as the language recognized by this machine. And you do it in two phases. Firstly, by proving that every string that's recognized by this machine is also recognized by this machine, which means that the language of the non-deterministic finite automaton with epsilon transitions is included in the one of the deterministic one, because every string recognized by the NFA-epsilon is also recognized by the DFA. After that, you need to prove that every string that's recognized by the DFA is also recognized by the NFA-epsilon. And once you've done both of them, then it means if you have the implications in both directions, the only possibility for that to work is that they are equal. And so they are equal, and you've finished your proof. So as I said, this is a proof that is, it looks so trivial and boring, and why do we waste time on this if someone else is doing it? And it's a whole different story if you are doing it. So you will be able to do fine if you have these things as definitions you can readily produce yourself. This is first of all the proof that the stuff in the NFA-epsilon, anything the NFA-epsilon recognizes is also recognized by the DFA. And so we have two cases. You have it on your handout, it's probably more readable than on the screen. The first case, so let's say x I need to work with a string, and I'm going to prove that x is in Lm implies that x is in L of Pm. So I might think of x as being a sequence of the symbols in the input alphabet sigma. But writing it out this way does not count the case where x might be the empty string. So let's first get that one out of the way. If x is the empty string, and the empty string is in the language recognized by the NFA-epsilon, then this means that there exists an epsilon transition to some state q which belongs in F, the set of finishing states. That is a direct consequence of the empty string being recognized by the non-deterministic automaton. So in this case, this means the set S prime, which was defined, what did we define it as? We defined it as the set of all the q's such that there exists something from S to this q prime with an epsilon transition will include this q, because this q enjoys this property. So Q is in S prime. So this means that there is an S prime intersection F includes the element Q. And so it is not empty. And so S prime is a member of the accepting states of my, yes? Okay, let me check other colors and see. You tell me if they are better. Is this better? Or this? Or that? I think I can make white if you like, if I press enough buttons. Which is best? White, okay. So, thank you for that. Did you miss everything I did up to now? Yes, great. Okay. So, how can I fix this without redoing it from zero? Because we really have other things to do as well. Just go and read this, which is probably going to be quicker. If the empty string is recognized by the NFA, then there exists an epsilon transition from the starting state to some state that is an accepting state in F. And if there is this state, then because of the existence of this transition, this state Q is part of the ones that are in S prime, because the definition of S prime, if you can produce that yourself, but if you can't, there should be a reminder here. The starting state was the set of the states for which one of these existed. So Q prime enjoys this property. So Q enjoys the property of the Q prime variable in here. So Q is a member of S prime. So if Q is in S prime, and I cannot write in white on this, so I had better choose one of the other colors you like, otherwise I will not be able to flip between the black background and the white background. Which other colors did you like? The yellow, maybe? Yellow is going to be unreadable on this too. Which color works on both? Green? Is it okay? Say yes or no? Yes. Okay, good. So let's use green. Then this means Q is in S prime. And so this means that S prime, because Q is also in F, Q is in S prime and in F, then the intersection S prime inter F is not empty, because it contains at least Q. And so because the sets that had a non-empty intersection with F were members of F prime, this means that S is in F prime. I mean, he skips a few passages, but that's what he says. And so if the starting state of my DFA is accepting, then it means the empty string is accepted by the DFA. And so that's the empty string dealt with. So next thing I have to do is to do the non-empty string. And the non-empty string what do we do with the non-empty string? Let's start again. And with the non-empty string here, A1, A2, AN, if this non-empty string is recognized by the NFA-epsilon, then I can produce a sequence of transitions. These with the double arrow would be inclusive of the epsilon transitions that are hidden, that goes through a number of the states in the NFA-epsilon, Q1. I mean, I call them arbitrarily. I'm saying that there exist some states, and I decide to call them these names. The one reached after A1, I'm going to call it Q1. The one after A2, I'm going to call it Q2. The one after AN, I'm going to call it Qn. A sequence like that exists because this string is recognized by the automaton, which finishes in a state Qn that is a member of the accepting states. I know that this sequence exists, and I say, what does happen when I feed the same string into the DFA? Well, what happens is that I'm going to start from the starting state. From the first symbol, I'm going to go into some state. The second symbol, I'm going to go into some other state. Because it's a deterministic finite automaton for every symbol, I will definitely go to some state. And I will end up in some state Sn. Now, as far as I know at the moment, there's no relationship whatsoever between the Q and the Qi's and the Si. However, if I think about it, the definition of delta, which you should be able to produce by heart, of course, and which, if you can't, I have brought up here, and I have to bring forward. The definition of the next state says that the next state S1 is the set of all the Q primes such that there exists a starting state that has a transition that takes me to this Q1. Now, in this case, I know that this exists. So there exists a starting state in S prime, namely S, such that the transition with A1 in the NFA takes me to a state Q1. So Q1 is a member of this S1. S1 is some state in the DFA, which is a subset of states of the NFA. And I know from this that it contains Q1. So I can write from this, I can write that Q1 is in S1. If I redo this reasoning, I can say that Q2 is in S2, blah, 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 all the way to Qn is in Sn. But Qn was also in F. And so if Qn is in both in F and in Sn, then Sn intersected with F is not empty. And so that this means that Sn is an accepting state for the DFA. And therefore, I have produced a derivation in a sequence of transitions in the DFA that starts in the starting state and finishes in an accepting state. So consequence of this was that Sn was a member of F prime. And therefore, this string A1 AN is also accepted by my DFA. Right? And that's it. And now I have to do the reverse implication, so going the other way, which I do on the next page. And again, first I get the empty string out of the way. I have to say, OK, if X is accepted by the PM, then X is accepted by M. So if X is the empty string and X, as the empty string, is accepted by the DFA, then the only way this can happen is if the starting state is also an accepting state. So the starting state of the DFA S prime is an accepting state, belongs in F prime. So if I'm in this situation, then for being in F prime, if again I bring up this thing which needs promoting to the front, you are in F prime if you are a subset of states that has a non-empty intersection with the set of accepting states of the NFA. So if starting state S prime is in F prime, it means there exists one state of the Q states inside this subset of states that is also accepting for the original NFA. So call this state Q. So if Q is in F, is an accepting state, and Q is also in S prime, for being in S prime, then it enjoys this property that there exists an epsilon transition from S to Q. This must exist because Q is in S prime, and Q is in F because of what I just said, non-empty intersection, and therefore the epsilon string, the empty string, is recognized by the NFA because there's an epsilon transition between it and an accepting state. And so I'm happy for the empty string. For the non-empty string, again, I split it into its n constituent symbols with n non-zero. If it is recognized by the DFA, there exists a sequence of transitions like the one we had in the previous slide, which said in the deterministic finite automaton, I can go with a deterministic arrow A1 to some state S1, A2 to some state S2, blah, blah, blah. And with AN, I get to the state Sn, which is going to be an accepting state for the DFA. So if I finish in a state that is accepting for the DFA, then this Sn has a non-empty intersection with the set of accepting states of the original NFA-epsilon machine. So this non-empty intersection must contain at least one element. Let's call Qn this element that is in the intersection of any element that's in the intersection of Sn and F. Any accepting state in Sn, I'm going to call it Qn by definition of Qn. Qn has the property that it is in the Sn inter F. And then, if I look at this definition of the delta SA, so this one had an Sn minus 1. So all this stuff here is the truth. This is my hypothesis, that the string is accepted by the DFA. So this is not stuff I'm making up. This is all true. Then I have deduced that there must exist a Qn inside here, which is also an accepting state for the NFA. And because of this, if I read this with this, then this delta of Sn minus 1 An, if I rewrite, delta of Sn minus 1 An must be equal to the set of Q primes in Q, such that there exists some Q in Sn minus 1 for which there exists a transition Q An Q prime. Right? So I know that Qn belongs in Sn. So this Qn, I know there exists one. I've already convinced myself of that. And so this is a Qn which is a member of this set, and all the members of this set enjoy this property. So there must exist some Q in Sn minus 1 for which there is a transition from Q to this Qn. So there must exist a Q such that there exists. This must exist because this Qn is in this set, so it enjoys this property. It exists, okay, well, I'll call it, what am I going to call it? Obviously, Qn minus 1. Because I know it exists, I'll write it here in a convenient way, and this belongs in here. And I can keep doing that going backwards, and for every S, I can say there must exist some state in the original machine that belongs in this state. So I go all the way here, and there exists a set Q1 in S1 such that a transition here takes me there. So with the same reasoning, there must exist some Q0 in S prime such that this transition takes me here. But if Q0 is in S prime, the definition of S prime, you have to recall the definition of S prime, which was that there exists, for every element in S prime, for every Q prime in this S prime, there must exist an epsilon transition from S to Q prime. So there exists, I deduce from this, a transition from S to Q0 in the NFA. So ultimately, I have produced a sequence of S epsilon to Q0, A1 to Q1, A2 to Q2, blah, 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 to Qn, which is a member of F. And so I have made a transition of non-deterministic arrows in the NFA from the starting state of the NFA to an accepting state of the NFA. And so I proved that this damn string also belongs in the NFA-epsilon, which closes the circle and takes me where I wanted, to say that the two machines recognize exactly the same language.